Ladies and gentlemen of BlueHat 2025, trust nothing.
Hello, BlueHat. Welcome to my session. I'm Maor Abutbul, a vulnerability researcher at CyberArk Labs. Thank you for having me, and thank you for coming. We'll start with the question. What would you think if I told you that your identity would be held by your system admin? That's trivial, right? But what if I told you that your identity would be mine, or any user on your identity provider? That's scary, right? By the end of the session, you will find out how. In this session, I'm sharing not only success stories, but also tools and techniques, rabbit holes, and failures. You may ask why, because these are great learning opportunities. We'll start with the GET request. So, who am I? I'm Maor Abutbul, a father, engineer, researcher, and a gamer. Rumor has it, I'm not the only gamer here. Around 8 years ago, I transitioned from engineering to research. Today, I'm a vulnerability researcher at CyberArk Labs. My team's main focus is on open source and identity-related systems. We share our work internally to make our products more secure, and externally via blog posts and talks to give back to the security community. Our agenda for today. I will highlight key items from 2 research projects we did on 2 open source identity providers, Keycloak and Authentik. Each part will start with a technical background to set a common ground for everyone, and then a dive into a technique or a vulnerability. I will also show demos exploiting the vulnerabilities we found. Part 1, Keycloak research. So, what is an identity provider? An identity provider is a system that manages digital identities. In our case, users. The IdP handles managing users from users creation and login pages to enforcing password policies. They make the developer's life easier. By integrating with an IdP, you don't need to handle users, manage the passwords and expiry. The IdP manages it for you. Web rates conditions. Let's define the problem. Web servers processes requests concurrently. So multiple requests arriving and attaching it with the same data at the same time can cause unintended behavior in the application. We start with limit overrun rates conditions. They enable you to exceed some kind of limit imposed by the business logic of the application. Examples will be redeeming a gift card multiple times, or withdrawing or transferring cash over a balance. We'll start with an example logic. This is our example logic. A request arrives with a discount code, and if the code is not used yet, it will be accepted, and the discount will be applied. Then we set the limit, the already used variable, to true. Then a second request arrives with the same discount code. This time, the code used variable is used. Then it will be rejected. Generally, this is the expected behavior. Let's look at the same requests in the race flow. In the race flow, both of the requests arrive at the same time. And because of concurrency, they are processed at the same time. In this time window, the code used variable is not set yet, leading to both of the requests being accepted and the discount applied twice. This is the race condition. The time between the check and the update is called the race window. In this window, we can exploit this issue. So how can we test remote servers for race conditions? The single packet attack. The single packet attack is a technique developed by PostRigger. It allows you to encapsulate or package multiple requests on a single TCP packet. Just a quick note about this part. This is a side quest, so if you lose me on the way, don't worry. We will get back to the Keycloak findings and demo later. So, generally speaking, the algorithm collects all of the relevant requests, sends most of the data without the last bytes, waits a few milliseconds, and then sends the last bytes of each request in a single packet. And that's it. The single packet attack algorithm, I don't care. Show me how. To use the single packet technique, there are a few tools we can use. Burp repeater, turbo intruder, and more. Today I will cover the first option, using burp repeater. We start by sending our request to the repeater. Then we edit each request. And then we create a new tab group. While creating a tab group, we select the relevant requests. These groups are requests to be sent together. Then, in the arrow near the send button, we select the option to send group in parallel, single packet attack. And that's it. Now you can test web applications for race conditions. Single packet, many requests on a single packet. Come on, that didn't fit me. My understanding. From what I know, in HTTP version 1, the data is transferred on a single stream. So if we send multiple requests, they will just get mixed, and the server won't be able to pass them. Then I was thinking to myself, it would be cool to inspect this traffic in Wireshark. But not so fast. The single packet attack is an HTTP version 2 only mechanism. HTTP version 2 uses TLS. OK, so let's decrypt. This sentence took us into a journey. And in the end, we found the following GitHub tool. Using this tool, we could extract the burp traffic, and then we could read the traffic in Wireshark. So we have the secrets for decryption. Let's inspect some packets. We start with an HTTP version 1 traffic. In HTTP version 1, the traffic is sent in clear text. So the data is transferred ASCII encoded on the wire. As can be seen in the image, the literal characters GET are sent ASCII encoded on the wire. In HTTP version 2, messages are called frames, and the data is transferred in binary. As can be seen in the image, the get request method here is translated to the 82 X value, in this case. In HTTP version 2, a new feature was introduced called multiplexing. Each frame has stream ID. These IDs represent different channels, which can distinguish different messages. This feature also allows sending multiple requests on a single packet. So let's look at a single packet attack. Essentially, we are sending 3 different GET requests on a single packet. And that's it. That's the single packet attack. Some key takeaways from HTTP. HTTP version 2 is binary, using frames and streams. Using streams permit multiple requests and responses to be sent simultaneously. This feature allows the single packet attack to work. OK, let's evaluate our learned technique on Keycloak. Our first target, Keycloak, is an open source identity provider maintained by Red Hat. It's the upstream of Red Hat single sign-on. Let's dive into our first story. Everything is multi-step. Here, our journey started by inspecting the Keycloak database. We found that the users table is separated from the required actions table. As can be seen in the image, the verify email flag is maintained in a separate table, different from the users table. So this meant that on user creation, no email verification is required. Let's inspect the user creation code. As can be seen in the snippet, first, a user entity is created, and later in the code, the required action is updated. This is our race window. So we speculated, can we gain unauthorized access using an arbitrary email and just create user and log in without email verification? It means that if we made a request with the register and the login in a single packet, we could log in without email verification. This test required us to create some burp macros, which allowed us to make this attack, create a registration and a login request on a single packet. So let's race against user creation. We are working with a debugger, stopping at the relevant source code, then checked the database status directly with no success. We lost the race against user creation. We lost the race, but this seemed like a great opportunity to understand why, and more importantly, to understand how we can avoid race conditions. So using debugger breakpoints and activating ORM logs, we found the missing piece. In the logs, we see the following 4 key items: auto-commit disabled, insert into users table, insert into required actions table, commit. Auto-commit disabled means that the application is using transactions. Transactions means that the database is updated in one shot or not. This feature, the transactions, prevented us from gaining, in this case, prevented us from gaining unauthorized access to the system. So with race conditions, everything is multi-step. Well, sometimes. But now we know how to find and avoid race conditions. Let's look at our first Keycloak demo. Keycloak initial access token limit overrun. We'll start with some background for this demo. In Keycloak, an admin can create API tokens for developers. The developers later use this API token to create client applications on the system. On creation, the admin set a maximum limit for this token. In this case, we set it to 2. It means that the developer can create maximum 2 clients on the system. Then he sends this API token to the developer. The developer uses this API token to create clients. And then when using this API token, the remaining count is updated. Let's look at the demo. We start by creating an initial access token and set the limit to 2. We copy the token and send it to the developer. The developer will use this token and make API requests. He also transfers his traffic to his burp proxy. And we created one client, client 1000 in this case. We will now send the request to burp repeater. And we will modify the requests. And we will create a few more requests. And we create a new tab group. And we give it a name. Now we set the option to send group in parallel, and we send all of the requests together. Let's see how many clients were created. And we can see that 4 clients were created. We can also see that the remaining count includes a negative number. So the math list is working. In case you missed it, we were able to create 5 clients using a token limited to create only 2. And that's it. Thank you. To summarize this part, we reported the issue to the Keycloak team. They confirmed it, made it public, and fixed it. Some takeaways from this research. HTTP request processing isn't atomic. HTTP version 2 is binary, using frames and streams. The single packet attack can be used to test web applications for race conditions, and the same system can include overlooked areas for race conditions. OK, that's it for this part. If you're interested in learning more, check out our Keycloak blog post. You can't always win racing the Keycloak. In the blog, I cover these race conditions and more. OK, let's dive into our next part, Authentik research and ORM leaks. In this part, we'll start with a technical background, and then we'll dive into 2 vulnerabilities we found, and hopefully we will have a live demo. Let's get started. Object relational mappers. Object relational mappers are a programming technique that enables you to work with databases, with relational databases, using an object-oriented programming language. They allow you to manage data without writing SQL queries. In ORMs, models define the structure of stored data. In the image, we can see a model declaration defined in Django, a Python framework that includes an ORM. So our new target, Authentik, is an open source identity provider maintained by Go Authentik.io. Authentik is a Django project. We'll now dive into our first Authentik vulnerability, sensitive information leak. We'll start with some background for this part. In Authentik, certificates can be used for 2 main functions. The certificate that is stored on the Authentik web server itself, used for HTTPS communication, and when configured as identity provider, to sign auth tokens. Here, our journey started with an admin user. We found that an admin can upload and generate certificates. Admin can also download certificates and private keys. So far, all good. At this point, we speculated, can a user download the private key? So we tried. And whoops, we found that not only any user can download the private key, no authorization is required at all. So anyone can download the private key. But we do have a limitation here. The internal UUID set by the Authentik server is required for this request. OK, so here we were thinking, how hard can it be to leak a UUID? But before we dive into this question, let's see if we should care. So a private key can be leaked. Should we care? An attacker possessing the private key can impersonate the Authentik web server itself, and by that phish users and admins. And also, it can impersonate users' tokens, and by that, gaining access to any system trusting Authentik. So with our motivation set, let's get back to our question. How hard can it be to leak a UUID? This question took us into the rabbit hole. We tried to leak by a few methods. At this part of the research, we already knew there are many API endpoints on the system. We also noticed that some APIs are leaking some internal UUIDs. So we speculated there must be one API in which we could leak this UUID. We tried each API in the specification, but this attempt failed. Then we encountered this excellent article by Eltam. Defined a new class of vulnerability, namely ORM Leaks. This article is about how insecure use on of ORMs can lead to information leaks. In my words, this technique allows attacker to leak data like SQL injections, but provided by the ORM. OK, let's find ORM leaks in Django. So to find ORM leaks in Django, the pattern we are looking for is using the filter method with the unpacking operator, double asterisk, applied to user supply data, allowing us to leak some internal data. And in our case, hopefully, our UUID. So we were looking, and we found a promising ORM leak instance. In the events log API, this API endpoint, the events per month API, this API endpoints can be accessed by any authentic user. As can be seen in the image, the user supplies query parameter, get parameter query, is loaded into the filter method using the unpacking operator. So we found a random API. What is it about anyway? This API returns timestamps and values. Each value represents the number of occurrences of the log in the relevant time slot. It is used by the Authentic UI to show event hits in each time slot. So we found an event log leak. Is it relevant for us? While inspecting the authentic log, while inspecting the authentic events log, we found the following log entry. When an admin uploads a certificate, the certificate UUID is get logged in the event log. Notice that the key data is masked here, so we can't leak it from here. Also notice that the content we are looking for is under context diff KPUUID new value. Let's try to exploit our ORM leak. Here's a typical request to the leaking events API. If a log entry is found, a non-zero value is returned. The content we are looking for is under context diff KPUID new value. So we updated the request to include a regex query to exploit the ORM leak. When using this request, notice the response. If it includes a number different than 0, then we found a log entry. With this API behavior, we have an oracle. Let's look at the demo. Using this oracle, we were able to leak each next character from the API, and eventually the full UUID and the private key. Thank you. You can't always win. After exploiting this issue, creating a POC, we tried to access this API using a normal user's permissions, but this attempt failed. We found that permissions are required in the database. But hey, now we all have a new tool in our toolbox. To summarize this part, we reported the info leak issue to the Authentik security team. They confirmed it, assigned CVE, and fixed it. And now, as promised, Authentik privilege escalation and live demo. Here, our journey started with a regular user. We found that a user can create API tokens for himself. He can later use this API token to access the Authentik API. So we created a token. Here we noticed that each token has expiration dates. A user can copy his token. A user can also edit his token. This seemed like an interesting functionality. In Authentik, edit means update. So a user can update the token description, and by default, the expiration date is updated. So we decided to inspect the token update request. When updating the token, we noticed an interesting JSON key in the response, the user object. This response led us thinking, what if we try to update the user? So we add the user key and set the value to 6. And we will now look at the demo. All right. So we start with logging in as a normal user. I'm copying the cookies so we can make the request easily from our BERT proxy. And it's also scripted, so it will be faster than me. Now let's look if the user has tokens and the user don't have any tokens. We start by creating a token, essentially. And the token was created for our user. Then we will request the API key. And we got the API key. We'll use this API key to query the version API. And we got a regular response from the API. Just a second, let's see if the user has tokens. And the user has this token. Now we will update the user. And it seems like the user is updated, and we have a new username. Let's try to use this user. Anyone wants to guess the password? 1, 2, 3. Nope. Anyone else? Admin. Nope. Well, why guessing if we can set? Let's see if we can use it. And we have admin access to the system. And that's it. Let's get back to the slide. Thank you very much. So we don't need it. So we have an admin API key. We have full control of the system. To summarize this part, we reported this issue to the Authentik security team. They confirmed it, assigned CVE, and fixed it. If you are interested in learning more about this research, check out our blog post. Let's be authentic. You can't always win. You can't always leak ORMs. In the blog, I cover these 2 vulnerabilities and more rabbit holes. Let's conclude our session. In part 1, we covered our Keycloak research. We started with the technical background, then got into web race conditions, the single packet attack, and HTTP version 2. Then we evaluated our technique on Keycloak, showed two scenarios, one which failed and one which succeeded. In the second part, we started with the technical background on object relational mappers, then got into the private key info leak and ORM leaks, and we concluded with our privilege escalation and demo. Research takeaways. HTTP request processing isn't atomic. HTTP version 2 is binary, using frames and streams. The single packet attack can be used to test web applications for race conditions. For developers, ensure sensitive endpoints make state changes atomic, in the API as well. Double-check access restrictions on sensitive endpoints, like the certificates. Avoid direct manipulation on tokens. And when using ORMs, be aware of vulnerable patterns and safe use. Some my friend says, oh, one more thing. In Authentik, when using admin privileges, we found an interesting functionality. Built-in impersonation. This functionality allows the admin to log in as any user on the system. So your identity is mine, or any authenticated user for the system. Thank you very much. For more info, check out our CyberArk research blog. For any feedback and question, feel free to contact me after the talk or via LinkedIn. Thank you very much.